Hello, everybody, again. So, of course, I wasn't looking at the schedule, and actually, we have 2 talks from Luis. It's better than 2 talks from me, so that's good. Essentially, what Luis is going to talk about first is this idea of risk mapping. So we go from getting our kind of raw picture of each component to a better picture of the actual dynamics of the disease as well as we are able to replicate it. So he's going to talk about that first and then about model evaluation. So here we go with Luis. Luis, it's all yours, and I will be here if you need me.
Thank you, Tom. Thank you. And hello, everyone. I'm going to share my screen. So this one. And I'm going to talk today about something that I really like, but rare to see in the literature. That sorry. Okay, it's about beyond just suitability for species, and we are going to add more information to our suitability maps, adding socioeconomic data, transportation routes, disease intervention information, and we are going to see that using such information, we are improving the interpretation of our maps. So these are the topics for this talk. We're going to talk about people density, how it affects disease spread, people movement, and going to give 4 examples. And finally, we are going to see how disease intervention information is affecting the geographic distribution of diseases in real events. So let's talk first about people density. The people density impacts the geographic distribution of diseases. To begin, I would like to share with you these 2 links from which we can collect information of human population values by pixel in the geography. I'm going to do this exercise in this presentation, in this talk, so you are going to see some links across the slides from which you can collect data. So I hope this is going to be useful for you. The first example about the use of human density and diseases is from measles in Niger. And this figure is showing the study area extent in Niger. You can see the white spots, and the meaning of those spots is the nighttime light values in the land. So what the researchers found is that more light is associated with more human density, and besides, more human is strongly associated with more measles cases. So using that information, they use light values to identify those areas with measles or that are vulnerable for measles transmission. This is a link from which you can collect nighttime light values to use in your research. So finally, this is a map from which they show the nighttime values across the study area, and you can see easily that the areas with high night light values are easily identified. So the authorities that can use this kind of information to identify such hotspots from which interventions are required, or education or vaccine should be implemented. Now let's talk a bit about people movement. The same case, people movement affects the geographic distribution of diseases. I would like to start showing this map, this global map of the air international travel in 1933 and 1933, and you can see that there are just few routes at that moment. Sorry for this. And so just few people was traveling across continents and across long distance. But now the situation in the last years has been changing a lot. So you can see that the international is very high nowadays, and there are a lot of people and products traveling across countries and across continents. So there are more chances for diseases translocation, and this is strongly related, or we can use information from biological invasions to understand how can this happen. In fact, there are some phenomena that we can learn from biological invasions that we can use to understand how spillover events could be translating to epidemics. This graph is showing how has been increasing the number of malaria cases in humans that travel from endemic areas of malaria to Europe. And here you can see that across the time, the number of reports of imported malaria in Europe has been growing, and this could be related to the improvement and the facilities to travel across the world. So there are several examples of this situation from the most studied diseases, including malaria and rabies, from which we have several cases of important rabies, for example, from people or from pets. And these patterns of people movement could be categorized according to the time of the movement. What I mean is that there are some people that move daily, while there are others that move according to seasons. And here I would like to use as an example the people in Guatemala that travel from the north to the south of the country, from which the social and the environmental conditions are pretty different, but they do this massive movement to harvest sugarcane or coffee, for example. So that's an example of seasonal people movement. But there are another kind of patterns of movement that we can categorize according to the time in daily, periodic, seasonal, or long-term movement. And here I include a link from which you can collect information of people displacement. It's not very displaced. Oh, there is a lack of a C, but no, please do not notice that. From that link, you can collect information on what is happening about the movement of people. It's not very friendly to collect the data, but it's a first step to identify the current or historic situation of that phenomena in several areas in the world. There's another emergent field with a lot of data that I feel it has been misused, and is the using of mobile phones to establish the movement patterns of human populations. Here, the first figure is showing the distance, the geographic distance, and the patterns of movement for several mobile phones. So we can do this kind of analysis in batch for a lot of people to see massive patterns. While in the other hand, we can do this kind of analysis at individual level. And we can do these measurements according to even hours. So there is a lot of data that is there available. Sometimes it's a bit hard to obtain the data because there are a lot of legal implications related to it. So usually in this kind of exercises, the researchers says that they are not using the names or the cities. So for example, you can see here that for both figures we cannot identify the geographic location of the study. So because there are several implications when using that kind of information, but the information is there and it can provide a lot of lessons to us. Some days ago, it was published a tool to simulating the spread of mosquitoes to anticipate the movement of malaria through the movement of cars. This is a very interesting approach that uses the roads and the highways from in one country of Europe. But this approach can be improved using, again, the information from mobile phones. In this example, the researchers found that the patterns are different across the time, the patterns of people movement. For example, in the top panel, we can see that the movement in Monday at the same time in the same location is pretty different compared to the movement of people in Friday. So we can start to use this kind of information because there are a lot of resources. I was in a presentation some months ago in which there was a researcher that shows that she collects information from Twitter to establish patterns of shopping preferences. And I didn't know that you can collect that kind of information at for free, and that is freely available, and it's very easy to collect that information. So there are too much data currently, and we must to start to learn how to use it in benefit of a healthier planet. Now let's see some examples. First, I would like to start with cholera. It is a project that we are running currently, and is a map of cholera suitability at course scale. Again, I showed it in one of the previous presentations, and it is the areas from which we can find cholera in seawaters across the world. And you can see that the geographic distribution is really broad for this pathogen, for this bacterium. Here you can see that this is a figure of the environmental space. So we can see the distribution of the points, but according to the environments. So, for example, here at the top in blue, we can see that Colombia is very close environmentally to Bangladesh, and that Bangladesh is, for excellence, the endemic area of cholera. That Brazil and Venezuela are sharing some space too, while there are other countries that are more far from the environmental conditions of the endemic areas. So considering that these environments are very close for these different coastal areas, we can start to be concerned about the potential translocation of the pathogen from the endemic Bangladesh to the novel environments of Colombia, Venezuela, and Brazil. So this is the map of cholera suitability, and you can see that there are several areas across the world that are suitable for the potential distribution of cholera. And something that is of concern for us is that currently global cargo ships are carrying cholera through the ballast water. Ballast water are the water that is collected from the starting point of the travel to provide balance across the travel of the ship. So once the ship arrives to the final destination, it put out the water, the ballast water. So there are several research done in this arena, and there are evidences of translocation of small animals and bacteria, including Vibrio cholera. So the suitability maps could be improved if we add to the environmental information the amount of transport between the endemic areas to the potential areas of invasion. And we can do this kind of analysis very easily. Some of the problems usually is that this information of ships traffic is usually not for free. So here I include a couple of links. Both of them have a lot of data about marine traffic, but both of them are not for free. But the information is there. So if you are working in a project that can pay that kind of information, maybe it could be a good idea to start exploring these kind of approaches. Now let's talk a bit about bloodborne rabies. And here we add information about demography, but not demography from people. We are going to use dog population information to establish some areas of potential bloodborne rabies spillover. I mean, the potential for the transmission from one species to another species. Well, to begin, Lyssa virus, according to molecular analysis, have an origin in bats, and then from bats they move to carnivores. So there are a ancient link between both species for the same viruses. And so what we did is that we collect the information of rabies cases of the bat species in Chile, the bat species Tadarira brasiliensis, that is carrying the strain number 4 of rabies. So what we did is that we modeled the cases of bloodborne rabies positive, and then we modeled the geographic distribution of bats, only bats, healthy bats. And we measure the overlap between positive bats and healthy bats, and we use that overlap as the potential distribution of bloodborne rabies in central Chile. So using that information, we know the suitability according to environments to the occurrence of rabies. But something that is interesting is that even when rabies is natural in bats because it co-evolved, there are some events in which some carnivores can be infected, for example, via ingestion or through the bites of infected bats, and it can get infected, the carnivores. And then the strain of the bats can be in the carnivores population with successful transmission. It was reported in the United States a successful spillover of bloodborne rabies from bats to carnivores, including skunks and foxes. And something that is pretty interesting is that the virus is not changing, is not evolving. The virus remains in the same in the same structure during these spillover events. And what is needed for the successful establishment in a new population is ecological factors, including carnivores density. So considering this, what we did is that we know that in Chile they have a huge problem of stray dogs. So, for example, this is a typical picture of Chile in which you can find several stray dogs across the cities. And that's very interesting because the country has a very good income, and people see these phenomena as natural. So they provide food, they provide shelter to these stray dogs, and that's why dogs have a lot of resources and populations can grow. At the point that currently the stray dog populations are from dogs that have huge sizes and very good healthy. So this is another typical situation in which is usual the mortality of people due to pack dogs attacks. No worries, this gentleman is not died because the person that took the picture helped him. What else? Okay, so what we did is that we use the huge amount of data from dog demography in Chile, and we collect data from these counties, so you can see that the information came from different areas across Chile, and we found that in the y-axis there are information from free roaming dogs, the proportion of free roaming dogs, and that more education means more free roaming dogs. People release, even when they have education, they release the dogs and they have the dogs unleashed. And more income means more free roaming dogs. And something surprisingly true is that when people have more dogs, they tend to have without supervision, so the dogs can roam freely. So this is a very interesting issue about the culture of dogs in Chile that could provide a lot of information for our maps of rabies. So we use this information with the information of rabies suitability to obtain this map, in which we categorize the level of dogs density to provide some levels of risk for rabies spillover to dogs. And we establish the counties that have more area of risk in central Chile, and we can see that the capital city of Chile has the more area as risk. And this is so after we made this model and this risk map, we add the information of positive dogs from the last years. This information was not used to calibrate the models and is used only to show and to test a risk map. And what we found is that all dogs fell in areas of risk of rabies spillover, and all dogs except one fall in areas of high risk of rabies spillover. Only one fell in medium high risk rabies spillover risk. So this information is giving us more clues about what could be happening in the near future. So the next example is about plague, and plague is known to be related to the poor people. So we use socioeconomic data to model plague in Pernambuco, in Brazil. And these are the areas from which a plague has been reported in Brazil, and these are the hosts that are related to rabies in the system. So here we have a bunch of rodents, but some mesocarnivores too, including marsupials as opossums. So what researchers did is that they used this information to model all the potential distribution of these reservoirs as an approach of potential areas for plague. But this was the study area that is in the left, and I like this example because the study area was based according to geographic barriers, and then the researchers cut the study area of interest, that is Pernambuco in East Brazil. But usually what we do is that we establish the study area according to political boundaries. So we should start to think more biographically. So this is the area of interest after the models, and you can see that there are high areas of richness that could provide more risk and areas with less number of species. And this is the Human Development Index that is related to education, health, and income of people. So when we have less human development index, we can start to thinking in more risk. So what they did is that they used such information to establish areas of risk, more richness of reservoirs, and less human development index was traduced as or translated as risk of plague. So they found these areas with more risk values, and then they were to the field to collect a serum of some dogs, and they made a review of cases, human cases and animal cases of plague in the last years, and they found this. So the risk map was giving some clues of what was happening in the geography of plague of Pernambuco. So apparently this information added to the suitability maps can help to give more information and to give more priorities to some areas. Finally, in the example of Ebola, Ebola is currently in the news, so I guess that it's important to talk a bit about it. And here we're going to add the information of traffic. This is the current distribution of airports in the world. So you can see that we have airports, and the connection of the people is very, very high in nowadays. But what we did is that we established the environmental distribution of the airports. So here, each point in the left means one airport in the geography, or several airports in the geography that are sharing the same environmental value. So here we are looking the airports in the geography, and here we are looking them in the environmental space. To exemplify this and make it more clear, what I did is that I collect a bunch of airports that were together, but when I see them in the geography, this is the sum of the area that I put in the environmental space. So you can see that all these airports here are close environmentally. They are sharing some similarities in the environment. For example, it could be a very similar temperature, a similar precipitation, but in the geography, they are really, really distant. So even when they are distant geographically, they are close environmentally. So we should start to live a bit the paradigm of the geography. So another example of living the paradigm of the geography is this example in which the researchers use airports and distance of airports, but they do not use this usual geographic distance. Just a parenthesis, this is a couple of links to collect this kind of air traffic information. So, close parenthesis. So this is the distance, the geographic distance between airports. But what they did is that they measure the distance according to the flow of flights. For example, there are some countries that are close because they have a lot of flights, while there are others that are far because there are not direct flights between the countries. For example, this country here is close to these ones here, but is far from this country, from this airport here, because there are no flights, or I need several flights to go there. So this is a distance according to a flight flow. And the starting point is the area of the current outbreak of Ebola virus. So something interesting is this huge point here, this airport here, that is only at one step from the original point. So let's see this point here in the geography. And surprisingly, this is the origin of the outbreak, and the close point is this one. It's one airport in France. So you can see that more information usually is out of the paradigm of the geography, because according to the authors, there are more people that could be sick traveling from across this area compared to the people that can travel inside the country. So that's pretty interesting. So as a summary, you can see that we can use a lot of information of the movement of people according to the space and according to the time. And for example, here there are some information of traditional data, including surveys, or we can use modern data, including remote sensing data or GPSs or media information or mobile phone information. So I'm going to leave this summary here provided that was published by TATEM. That is pretty interesting to me and is a nice summary of these approaches. Finally, I would like to talk about disease intervention information and how it shapes the geographic distribution of diseases. Definitely, human intervention affects the distribution of diseases, because we could reduce the exposure of the disease, or we could intervene in providing immunity to the population, or we can reduce the number of vectors of reservoirs in the system, or we can change some practice. So intervention impacts. And one example of this is the distribution of rabies in the US. Here you can see that you can see here the distribution of the different strains of rabies in the US. Raccoon is one of the most important strains in the country. And this is one picture of bat-borne rabies in the US. So you can see here a very dispersed distribution of cases. But this is the distribution of raccoon rabies. Raccoon is a medium-sized mammal that is present in all the country. And something interesting here is that it has a very different distribution. And this distribution is limited by a campaign of oral vaccines across this line. So that's why the intervention is shaping this distribution of rabies in the US. So providing rabies vaccination, they are limiting the rates of transmission in this species. So this is an important factor to consider when we are mapping rabies in raccoon, for example, because we can see that there are differences in the intervention of people in this disease. So this is all for me for today, and I would like to acknowledge to Yuhie Chao, Daniela Po, Francisca Astorga, and Gian de Oliveira, because they provide information for this presentation. So thanks, everyone.
Thank you, Luis. Okay, so here's the deal. It's later than we thought. I think kind of all of the presentations this morning went a little bit longer than we had imagined. So what we're wondering about is maybe we should not do a question and answer session today and go on with the model evaluation, or we can do question and answer but leave model evaluation until tomorrow or Friday. The one bit of evidence in favor of the latter, which is to say do model evaluation right now, is that we have no questions so far.
Okay.
Luis, you want to go ahead with your second presentation, and then we, if any questions come in, we do them tomorrow morning?
Terrific.
Okay, then let's end this broadcast. Thank you, Luis, for talking about essentially translating between components and risk. And we'll be back in 5 minutes with a module on evaluating model predictions. Okay, So see you all in just a moment, and watch the Google Plus page for the links. Thanks, everybody. Thanks, Luis. Bye-bye.
Bye-bye.